All right. I forgot that I have like a appointment at 4. So I gotta leave around like 3:45 for that. So I figured I'd just hop on and get a quick 1 hour stream in here so that we can make some more progress on the advanced sockets. Advanced, what's it called? Advanced features, advanced topics for sockets. During my lunch break, I was doing a little bit more reading. I did this experiment where I ran strace on CP to see what it does when it's copying a file from A to B. Because we implemented it using the send file. And you can see here it's doing a copy file range. It did two actually. It did one that returned 71 and then another one that returned 0. So maybe that was a error because it gave the same range each time. But anyways, copy file range, I was kind of curious like what that was. And basically it's kind of like send file. It came after send file. So send file was like the original syscall that then spawned all these other types of syscalls like splice, VM splice, T, and now this one, which is copy file range. And I was chatting with AI a little bit about it, and I was like, well, why would you use this over send file? Because send file can do the same thing with file descriptors. And basically, like this copy file range, I wish they renamed it to be something different. But anyways, copy file range is optimized for operating on file descriptors, like real files. And it can do things like if the file is being copied, the source and destination of the file is on the same file system, it can do a zero copy, if that makes sense. Where basically it's kind of like a copy on write type copy, where it just points to the same data. So that's like a big optimization that you can take advantage of when you use CP. But if you use send file, the kernel is literally going to send the bytes. Read the bytes off disk and write the bytes back to disk. So much better to use copy file range if you're actually doing anything that copies ranges of files. Cool. Another thing to learn about. So yeah, we left off here where we're talking about TCP segments. So each segment is kind of like the data that gets put into the IP packet. So IP has like, source and destination IP addresses. So that can be routed across, a wider network. However, inside the IP packet, the data of that is what is known as, if it's a TCP packet, it would be a TCP segment. And that has concepts like port numbers, source and destination port numbers. So that's addressing the actual application on the host. IP is to address to the host. Port number is to address to the application running on the host. Sequence number is really important. We learned that the sequence number is basically the 0th byte of the sequence of bytes in the packet. So if there's 4 bytes in the packet, your sequence number might be 20. And then the next segment will have the byte number of 24 because those 4 bytes were sent out in the previous segment. So that's kind of what we have talked about so far. We haven't really addressed a lot of the other bits of the header, but that's the high order bits are what we already discussed here. So actually, let's go back here and we'll start from here because I don't know if we actually read these things yet. So let's start with format of a TCP segment. Figure 61.2 shows the format of TCP segments that are exchanged between the endpoints of a TCP connection. The meanings of the fields are as follows: source port number. This is the port number of the sending TCP. Destination port number, this is the port number of the destination TCP. Sequence number, this is the sequence number for the segment. This is the offset of the first byte of data in the segment within the stream of data being transmitted in this direction over the connection, as described in section 58.6.3. So it's in this direction. So that means that sending and receiving, it's a bidirectional stream. So they can both have their own independent sequence numbers. Acknowledgement number. If the ACK bit, see below, is set, then this field contains a sequence number of the next byte of data that the receiver expects to receive from the sender. Okay. So it's acknowledging everything up to that number. Header length. This is the length of the header in units of 32-bit words. Since this is a 4-bit field, the total header length can be up to 60 bytes, 15 words. This field enables the receiving TCP to determine the length of the variable length options field and the starting point of the data. Reserved. This consists of 4 unused bits, must be set to 0. Control bits. This field consists of 8 bits that further specify the meaning of the segment. Okay, if we go back to our diagram real quick. So acknowledgement number is similar to the sequence number. It's a sequence number that we're acknowledging as part of this packet going back to the sender, the original sender. These are zeros, so that's not really important. This encodes the length of the header itself. And then in the control bits, we got these things set. So we got CWR. I guess the important bit here is acknowledgement number. If set, then the acknowledgement number field contains valid information. So if it's not set, then we're not acknowledging it, then this acknowledgement number isn't really important. Okay, let's start at the top here though. CWR is the congestion window reduce flag. ECE is the explicit congestion and notification echo flag. The CWR and ECE flags are used as part of TCP's explicit congestion notification ECN algorithm. ECN is a relatively recent addition to TCP/IP and is described in RFC 3168. And in Floyd 94, ECN is implemented in Linux from kernel 2.4 onward and is enabled by the non-zero value in the Linux-specific proc_sysnet IPv4 TCP/EN. Let's see if we have that set. Cat out proc_sysnet. What does it say here? IPv4 and TCP ECN. So it's set to 2. So that must be the version of it that we're using. Urgent, URG. If set, then the urgent pointer field contains valid information. So if we go back a page here, there's an urgent pointer field. So if our control bit has URG set, then this has valid information, similar to how the acknowledgement number works. If set, then the acknowledgement number field contains valid information. PSH, push all received data to the receiving process. This flag is described in so-and-so. Reset the connection. This is used to handle various error situations. So that's another control bit, is a reset. And I'm familiar with that because the reset, when you reset a connection, it basically like resets the state machine of the connection. And usually it's like the final state of the connection. And you don't need to have a reset to have a broken connection. The connection could break. One of the sides could go away, just disappear. And then eventually the server will send a reset, or one of the sides of the connection will send a reset if it hasn't heard from the other side in a while. I say that because I know there's situations where, like, if you have a running system and you freeze all the active state of the system, like you hibernate the system, and then later on you thaw the same system, all of those connections will still be active on the thawed thing, but it's been gone, it's been frozen and thawed out. And in that time, the peers that it was connected with have gone away. And so all of its connections will need to be reset because it would have received the RST from the peer. Okay, SYN. Synchronized sequence numbers. Segments with this flag are set to exchange flag set are exchanged during connection establishment to allow two TCPs to specify the initial sequence numbers to be used to transfer data in each direction. So the handshake, the TCP handshake is a SYN, a SYN-ACK, where both this and this are set, and then the final one is just an ACK. So SYN, SYN-ACK, ACK. FIN is used for finishing the finalizing the connection. Used by sender to indicate that it has finished sending data. Multiple control bits, or none at all, may be set in a segment, which allows a single segment to serve multiple purposes. For example, we'll see later in that a segment with both SYN and the ACK bit set is exchanged during TCP connection establishment. Additionally, like when you're sending data, you can have you will have acknowledged numbers, acknowledgement numbers being sent back to the peer. Window size. This field is used when the receiver sends an ACK to indicate the number of bytes of data that the receiver has space to accept. This relates to the sliding window scheme briefly described in section 58.6.3. That was a very brief description because we went over it and I was like, yeah, this isn't terribly interesting to me. Checksum. This is a 16-bit checksum covering both the TCP header and the TCP data. Okay. Didn't realize it's both. The TCP checksum covers not just the TCP header and data, but also 12 bytes, usually referred to as the TCP pseudo header. The pseudo header consists of the following: source and destination IP address, 4 bytes each, 2 bytes specifying the size of the TCP segment. This value is computed but doesn't form part of either the IP or TCP header. 1 byte containing the value 6, which is TCP's unique protocol number within TCP IP suite of protocols, and 1 padding byte containing 0. So the length of the pseudo header is a multiple of 16 bits. The purpose of the purpose of including the pseudo header in the checksum calculation is to allow the receiving TCP to double check that an incoming segment has arrived at the correct destination, i.e. that IP has not wrongly accepted a datagram that was addressed to another host or passed TCP a packet that should have gone to another upper layer. UDP calculates the checksum in its packet headers in a similar manner and for similar reasons. See Stevens 94 for further details on the pseudo header. I'm kind of curious, like what exactly is in the pseudo header? Because I wasn't familiar with this concept, is in the pseudo header of a TCP segment. Temporary structure used only when computing TCP checksums. Okay. So it's not actually sent on the wire. He didn't really mention that in the book, so it's good that we asked the AI here. Its purpose is to protect against misdelivery by incorporating key fields from the IP layer into the checksum. So that means that these checksums need to be recalculated when you're going through NAT. Like when you go through network address translation, the source IP address will change. Destination won't, but source will. Which means that the checksum will be invalidated. The pseudo header, TCP header, data, padding. But the pseudo header ensures the checksum covers source destination protocol. What's protocol again? V6 or V4. Segment length. Even though IP has its own checksum, IPv4 only, TCP adds end-to-end protection. IPv6 pseudo header differences. IPv6 uses a similar idea, but with layer addresses. Source address, destination address, TCP length, 0 padding, next header field proto number. Does that mean when you go through a NAT device, it needs to recalculate the checksums because the source IP will differ between the peers? Yep. Do an incremental checksum update, which is faster. They adjust the checksum mathematically based on what changed instead of rehashing the entire packet. Wow. That means that the checksum that they used for TCP isn't like a hash, like a pure hash. This works because the internet checksums use one complement arithmetic, which supports efficient delta updates. That's pretty cool. That's pretty cool. All right. So that covers all of the. Oh no, we're at what? Urgent pointer? Yeah. Where is that over here? That is so weird. Oh, he's done a complete rewrite of this. He goes in TCP state machine and state transition diagram. He goes all, so this is all. What? Am I on the wrong? I'm on the wrong page here. That's what it is. Okay, so we read this. All right, now we're on urgent pointer. Okay, that's like totally on the wrong page. I was very confused there. Okay, urgent pointer. If the URG control bit is set, then this field indicates the location of so-called urgent data within the stream of data being transmitted to the sender or receiver. We briefly discussed urgent data in section 61.13.1. Options. This is a variable length field containing options controlling the operation of TCP connection. Data. This field contains the user's data transmitted in the segment. This field may be of length 0 if this segment doesn't contain any data, e.g. if it is simply an ACK segment. TCP sequence number acknowledgements. Each byte that is transmitted over a TCP connection is assigned a local sequence number by TCP. Each of the two streams in the connection has its own sequence numbering. When a segment is transmitted, its sequence number field is set to the logical offset of the first byte of data in the segment within the stream of data being transmitted in the direction over the connection. This allows the receiving TCP to assemble the received segments in the correct order and to indicate which data was received when sending an acknowledgement to the sender. To implement reliable communication, TCP uses positive acknowledgements. That is, when a segment is successfully received, the acknowledgement message, i.e. a segment with ACK bit set, is sent from the receiving TCP to the sending TCP. As shown in figure 61.3, the acknowledgement number field of this message is set to indicate the logical sequence number of the next byte of data that the receiver expects to receive. In other words, the value in an acknowledgement number field is the sequence number of the last byte in the segment that it acknowledges plus 1. So sender says, hey, here's my segment of X bytes, sequence number range N to N plus X minus 1. Receiver gets that, sends back an ACK of the segment, which is N plus X. Okay. When the sending TCP transmits a segment, it sets a timer. If an acknowledgement is not received before the timer expires, the segment is retransmitted. Figure 16.3 and later similar diagrams are intended to illustrate the exchange of TCP segments between two endpoints. An implicit time dimension is assumed when reading these diagrams from top to bottom. TCP state machine and state transition diagram. So we'll get to the diagram here in 2 pages. This is a diagram that I'm familiar with. It's very popular on the internet. If you search for TCP state diagram. Yeah, we get to read a textual version of it first. I feel like we need a page back and forth here. All right, maintaining a TCP connection requires the coordination of the TCPs at both ends of the connection. To reduce the complexity of this task, a TCP endpoint is modeled as a state machine. This means that the TCP can be in one of a fixed set of states, and it moves from one state to another in response to events, such as system calls by the application above the TCP or the arrival of TCP segments from the peer TCP. TCP states are as following. Listen. So that's known as passive open. Okay. Listen. TCP is waiting for a connection request from a peer TCP. So it hasn't connected yet. SYN set, the TCP has sent a SYN on behalf of the application performing an active open and is waiting for a reply from the peer in order to complete the connection. So we're trying to get to established. So we can be closed. This would be a client, and listen would be a server. So the client goes down this path, the server goes down this path. So the client says, hey, active open, I'm sending my SYN. Since it goes into SYN set state. And then the server then receives the SYN, goes into the SYN receive state. It sends the SYNAC. SYNAC then comes in to the client, makes it an established connection. It sends its ACK. Server then receives ACK, sends nil. And so they're both established now. So to read over on the text of that, I'll just read it here. SYN sent, TCP has sent a SYN on behalf of an application performing an active open and is waiting for a reply from the peer in order to complete the connection. The SYN receive, TCP formerly in the listen state, has received a SYN and has responded with the SYN ACK, i.e. the TCP segment with both the SYN and ACK bit set, and is now waiting for an ACK from the peer TCP in order to complete the connection. Established. So they both can transition into established. Established of the connection to the peer TCP has been completed. Data segments can now be exchanged in either direction between the two TCPs. Okay, so these are the established as data transfer state. So we do read and writes to the socket. There's this active close, and then there's a fin, passive close. Okay. So far passive open was a server, active open was a client. All right, so fin wait 1 should be this one here. So that would be an active close where the client is saying, hey, I'm done, fin. It goes into fin wait 1. The application has closed the connection. The TCP has sent a fin to the peer TCP. The TCP has sent a fin to the peer TCP in order to terminate its side of the connection and is waiting for an ACK from the peer. This and the next 3 states are associated with an application performing an active close, that is the first application to close its side of the connection. Fin wait 2, so it received the ACK to the fin, and then I think you can say fin and ACK at the same time. So you can go, yeah, exactly. You can go diagonally here. So sometimes it might just receive the ACK though, in which case it goes to fin wait 2, and then it has to receive the fin separately and also send its ACK, or it can just transition all the way in one packet this way into time wait. Or after it sends its fin, the other end of the connection might be doing an active close as well, and it sent its own fin without acknowledging this fin. In which case this end of the connection basically says, okay, I sent a fin, you sent me a fin, I'm acknowledging your fin, and we can just go into closing state. And then we wait for it to acknowledge that we sent our acknowledgement. It needs to acknowledge our original fin, basically, to go down to time wait. And then once we're in time wait, then 2 milliseconds. What is this? MSL? I don't know what that is. Basically, time wait eventually goes into closed. Okay. Let's talk about fin wait 2. The TCP formerly in the fin wait 1 state has now received an ACK from the peer TCP closing. Formerly, the TCP formerly awaiting an ACK in the fin wait 1 state instead received a fin from the peer indicating that the peer simultaneously tried to perform an active close. In other words, the two TCPs sent fin segments at almost the same time. This is a rare scenario. Time wait. Having done an active close, TCP has received a fin indicating that the peer TCP has performed a passive close or an active close. This TCP now spends a fixed amount of time in the time wait state in order to ensure reliable termination of TCP connection and ensure that any old duplicate segments expire in the network before a new incarnation of the same connection is created. We explain the time wait state in more detail in section 61.6.7. When this fixed time period expires, the connection is closed and the associated kernel resources are freed. So it waits a bit of time for packets to drop and everything to go away, and then it closes everything. Okay, so that is the active close. Then there's the passive close. So this would be on the other side. So the peer that was not doing the closing but receiving the closing. So we receive a fin that was sent here. We send our ACK. We go into close wait. Sorry. The TCP has received a fin from the peer TCP. This and the following state are associated with an application performing a passive close, that is a second application to close the connection. And then we send our own fin. We go into this last ACK state, and then eventually we receive an acknowledgement of our fin, which is sent here, going there, sent here, going there, or sent here, going there. We wouldn't be in this branch though, because this would be 2 active closes going at the same time, would be this branch here. So we either receive it from here or here. And that'll put us in the closed state. We don't have to wait in this situation, which is interesting. Okay, last act, an application performed the passive close, and the TCP, formerly the closed wait state, sent a fin to the peer TCP and is waiting for it to be acknowledged. When this act is received, the connection is closed and the associated kernel resources are freed. To the above states, RFC 793 adds one further, a fictional state closed, representing the state where there is no connection, i.e. no kernel resources are allocated to describe a TCP connection. In the above list, we use the spelling for the TCP states as defined in Linux source code. These differ slightly from the spellings in RFC 793. Figure 61.4 shows the state transition diagram for TCP. This figure is based on diagrams in RFC 793 and Stevens et al. This diagram shows how a TCP endpoint moves from one state to another in response to various events. Each error indicates a possible transition and is labeled with the events that trigger the transition. This label is either an action by an application in boldface or a string or the string receive, indicating the receipt of a segment from a peer TCP. As the TCP moves from one state to another, it may transmit a segment to the peer, and this is indicated by the send label on the transition. For example, an error for the transition from the established to the fin wait 1 state shows that the triggering event is a close by a local application, and that during the transition, the TCP sends a fin segment to its peer. Okay. In figure 61.4, the usual transition path for a client TCP is shown with heavy solid arrows, and usual transition path for server TCP is shown in heavy dashed arrows. Okay, that's nice to know. Other arrows indicate paths less traveled. Looking at the parenthetical numbering on the arrows in these paths, we can see that segments sent and received by the two TCPs are mirror images of each other. After established state, the paths traveled by the server TCP and the client TCP may be the opposite of those indicated if it's the server that performs the active close. Yeah. Figure 61.4 doesn't show all possible transitions for this TCP state machine. It illustrates just those of principal interest. More detailed TCP state transition diagram can be found at. Let's see if this is the actual link that is not dead. Oops. Hey, look at that. A lot more complicated, isn't it? Is the original. I don't like this diagram. You can't really look at it and be like, oh, it's so clear, you know. So I actually prefer the one in the book, although it might not be as technically accurate. All right, at TCP connection establishment. At the sockets API level, two stream sockets are connected via the following steps. See figure 56.1, blah, blah. The server calls listen to perform a passive open of a socket, and then calls accept, which blocks until the connection is established. Client calls connect to perform an active open of a socket in order to establish a connection to the server's passive socket. The steps performed by TCP to establish a connection are shown in figure 61.5. These steps are often referred to as a three-way handshake. Since these segments pass between the two TCPs, steps are as follows. The connect causes the client TCP to send a SYN segment to the server TCP. This segment informs the server TCP of the client's TCP initial sequence number, labeled M in the diagram. This information is necessary because sequence numbers don't begin at 0, as noted in section 58.6.3. Server TCP must acknowledge the client's TCP segment, SYN segment, and inform the client TCP of its own sequence number, labeled N in the diagram. So you got M and N sequence numbers. Two sequence numbers are required because a stream socket is bidirectional. The server TCP can perform both operations by returning a single segment with both the SYN and the ACK control bits set. We say that the ACK is piggybacked on the SYN. The client TCP sends an ACK segment to acknowledge the server's TCP SYN segment. Makes sense? The SYN segment exchange in the first two steps of the three-way handshake may contain information in the options field of the TCP header that is used to determine various parameters for the connection. See Stevens et al. Stevens, and Wright and Stevens for details. The labels inside the ankle brackets listen. For example, in figure 61.5 indicate the states of the TCP on either side of the connection. The SYN flag consumes a byte of the sequence number space for connection. This is necessary so that this flag can be acknowledged unambiguously, since segments with this flag set may also contain data bytes. This is why we show the acknowledgement of the SYN M segment as ACK M+1. Okay, TCP connection termination. Closing a TCP connection normally occurs in the following manner. An application on one end of the connection performs a close. This is often, but not necessarily, the client. We say that this application is performing an active close. Later, the application on the other end of the connection, the server, also performs a close. This is termed a passive close. Figure 61.6 shows the corresponding steps performed by the underlying TCPs. Here, we assume that the client that does the active close. Here we assume that it is the client that does the active close. These steps are as follows. The client performs an active close, which causes the client TCP to send FIN to the server TCP. After receipt of the FIN, the server TCP responds with an ACK. Any subsequent attempt by the server to read from the socket yields EOF. When the server later closes its end of the connection, the server TCP sends a FIN to the client. Oh, so this is like shutdown, where you can have one of the directions closed but the other not closed. When the server later closes its end of the connection, the server's TCP sends a FIN to the client TCP. The client TCP responds with an ACK to acknowledge the server's FIN. As with the SYN flag, and for the same reasons, the FIN flag consumes a byte of the sequence number space for the connection. This is why we show the acknowledgement of the FIN M segment as ACK M+1. Calling shutdown on a TCP socket. The discussion in the preceding section assumed a full duplex close. That is, an application closes both the sending and receiving channels of the TCP socket using close. As noted in section 61.2, we can use shutdown to close just one channel of the connection, a half duplex close. This section notes some specific details for shutdown on TCP sockets. I didn't even know you could do this. This is crazy. It's not very common, that's why I don't know about it. All right, specifying how as shut write or shut read write indicates the TCP connection termination sequence, i.e. the active close described in section 61.6.5, regardless of whether there are other file descriptors referring to the socket. Once the sequence has been initiated, the local TCP moves into the fin wait 1 state and then into the fin wait 2 state, while the peer TCP moves into the closed wait state. If how is specified as shut write, then since the socket file descriptor remains valid and the reading half of the connection remains open, the peer can continue to send data back to us. The shut read operation can't be meaningfully used with TCP sockets. This is because most TCP sockets don't provide the expected behavior for shut read, and the effect of shut read varies across implementations. On Linux and a few other implementations, following a shut read and after any outstanding data has been read, a read returns end of file, as we expect from the description of shut read in section 61.2. However, if the peer application subsequently writes data on its socket, then it's still possible to read that data on the local socket. On some other implementations, e.g. BSD, shut read does indeed cause subsequent calls to read always return 0. However, on those implementations, if the peer continues to write on the socket, then the data channel will eventually fill until the point where a further blocking call to write by the peer will block. With Unix domain stream sockets, a peer would receive a sig pipe signal and the epipe error if it continued writing to its socket after shut read had been performed on the local socket. In summary, the use of shut read should be avoided for portable TCP applications. The time wait state. The TCP time wait state is a frequent source of confusion in network programming. Let's go back to the diagram. So time wait is when we're stuck down here. Everyone's exchanged a fin act. The passive close has already gone to its close, and now the active close is for some reason waiting around. The TCP time wait state is a frequent source of confusion in network programming. Looking at figure 61.4, we can see that the TCP performing an active close goes through this state. The time wait state exists for several purposes. Excuse me. The time wait state exists to serve two purposes: to implement reliable connection termination and to allow expiration of old duplicate segments in the network so that they are not accepted by a new incarnation of the connection. The time wait state differs from other states in that the event that caused a transition out of the state to closed is a timeout. This timeout has a duration of twice the MLS, 2 MLS, where MLS is maximum segment lifetime. It is the assumed maximum lifetime of a TCP segment in the network. An 8-bit time to live TTL field in the IP header ensures that all IP packets are eventually discarded if they don't reach their destinations within a fixed number of hops routers traversed while traveling from the source to the destination host. The MSL is an estimate of the maximum number of the maximum time that an IP packet could take to exceed the TTL limit. Since it is represented using 8 bits, the TTL permits a maximum of 255 hops. Normally, an IP packet requires considerably fewer hops than this to complete its journey. A packet could encounter this limit because of certain types of router anomalies, e.g. a router configuration problem. It causes the packet to get caught in a network loop until it exceeds the TTL limit. The BSD socket implementation assumes a value of 30 seconds for the MSL, and Linux follows the BSD norm. Thus, the time wait state has a lifetime of 60 seconds on Linux. However, RFC 1122 recommends a value of 2 minutes for the MSL, and on the implementation following the circumvention, the time wait state can thus last 4 minutes. We can understand the first purpose of the time wait state, ensuring reliable connection termination. By looking at figure 61.6 in this diagram, we can see that 4 segments are usually exchanged during the termination of TCP segment. The last of these is an ACK sent from the TCP performing an active close to the TCP performing a passive close. Suppose that this ACK gets lost in a network. If this occurs, then the TCP performing the passive close will eventually retransmit its FIN, having the TCP that performs an active close remain in the time wait state for a fixed period. It ensures that it is available to resend the final ACK. In this case, if the TCP that performed the active close did not still exist, then since it wouldn't have any state information for the connection, the TCP protocol would respond to the resent FIN by sending an RST reset segment to the TCP performing the passive close, and this RST would be interpreted as an error. This explains why the duration of the time wait state is twice the MSL. 1 MSL for the final ACK to reach the pure TCP, plus another MSL in case a further FIN must be sent. An equivalent of the time wait state is not required for the TCP performing the passive close because it is the initiator of the final exchange in the connection termination. After sending the FIN, the TCP will wait for the ACK from its peer and retransmit the fin if its timer expires before the ACK is received. So if we go back to that diagram, so it's basically it goes into closed wait, it sends its fin, and then it goes into this last act, which is similar to the time wait, I guess. And then when it receives its act, it just immediately closes. And then this guy hangs out here because the act was sent, but we never get an acknowledgement of the acknowledgement. So we gotta wait around to resend it if we need. Okay. Here we go. To understand the second purpose of the time wait state, ensuring the expiration of old duplicate segments on the network, we must remember that the retransmission algorithm used by TCP means that duplicate segments may be generated, and that depending on routing decisions, these duplicates could arrive after the connection has been closed. For example, suppose that we have a TCP connection between two socket addresses, say 204 so-and-so port 21 and 200 port 5000. Suppose also that the connection is closed and that later a new connection is established using the exact same IP address and ports. This is referred to as a new incarnation of the connection. In this case, TCP must ensure that no old duplicate segments from the previous incarnation are accepted as valid data in the new incarnation. This is done by preventing a new incarnation from being established while there are an existing TCP in the time wait state on one of the endpoints. A frequent question posted to online forums is how to disable the time wait state, since it can lead to error address are in use when a restarted server tries to bind to a socket to an address that has a TCP in the time wait state. Although there are ways of doing this, it's better just to randomize one of the ports on the client. Like don't have the client reestablish on the same port. So although there are ways of doing this and also ways of assassinating a TCP in this state, i.e. causing the time wait state to terminate prematurely, this should be avoided since it would thwart the reliability guarantees that the time wait state provides. In section 6110, we look at the use of the so reuse adder socket option, which can be used to avoid the usual case of the error in use error while still allowing the time wait to provide its reliability guarantees. So, I mean, the better thing to do is just to not have the client reuse port numbers. Once it's done with the connection, have it move on to a different port number. Let's see here. You look like a spammer. All right, monitoring sockets with netstat. We will probably need to find an alternative for this because netstat does not exist anymore. No, I was thinking netstat. I guess we can install it, right? Pacman search for netstat. Small program written in C displaying NAT connections. So no. What is the replacement for netstat? Yeah. Man SS. Another utility to investigate sockets. Socket statistics, that's what it stands for. So that's a new version of netstat. So we'll come back to this once I'm back in the evening from my appointment. But yeah, monitoring sockets with netstat is a little bit dated. Using TCP dump to monitor TCP traffic, that's still valid because you can just dump packets and analyze them with Wireshark or do whatever you want. Socket options, get sock op and set sock op. I'm surprised we haven't covered that yet. So he's going to go into some detail there. The reuse adder option, inheritance of flags and options across accept, TCP versus UDP discussion, advanced features, out-of-band data, send message and receive message, system calls, passing file descriptors, receiving sender credentials, sequence packed sockets, SCTP and DCCP transport layer protocols. I've never heard of those. And then we're done with this chapter. Summary. Okay. Cool. I'm going to go ahead and break here. I got my appointment at 4. Will last until 5, and I probably won't get back until 6. So I'll probably hop on for another hour this evening just to see if we can wrap up this chapter. See how many pages we got here. We got 1, 2, 3, 4, 5, 6, 8, 9, 10. Around 10. I can do that in an hour. So cool. All right, I will be on this evening then, around 6 p.m. my time, to finish chapter 61. Sockets, Advanced Topics.